So today we are going to discuss something very interesting. We are going to discuss what is called the free expansion of a gas. Now we have learned how to use partial derivatives in dealing with thermodynamic systems, and in this setup we are going to use that knowledge. First, so what is this free expansion of this gas? So consider that I have a chamber which I have partitioned into two halves, and here in this half I have the gas particles which are contained over here. The other side, this part is vacuum. There is no heat exchange that is allowed, and what you do is you break this partition. What happens is that the gas then expands into this vacuum, and the final state is where the gas has occupied the whole of the volume. So initially the volume of this particular chamber was Vi, and the total volume of this chamber is Vf. Right? Now this phenomenon is also what is called a Joule expansion. It was first devised by Joule to figure out whether the internal energy depends on the volume of the gas. So the question now comes in that I want to see if there is a change in temperature. Please note that there is no heat, no work done in the system, and this implies, so there is no heat or work done, so that I have TdS is equal to du plus PdV for a hydrostatic system, and there is no work done, there is no heat, so this implies du is 0. So the internal energy remains constant. Now with this constraint, I want to see if there is a change in the temperature. For that, I write dt, an infinitesimal change, as del T del V. The volume is being changed over here because the gas initially occupied a volume Vi, and then it occupies a volume Vf. So this is the information that is given to me, but then this is U is being held constant, N is also being held constant, but we'll suppress that, and I have dV. This del T del V, U constant, is the quantity which we have to figure out. So let's see, let us apply all our knowledge on partial derivatives. How we can manipulate the Maxwell's relations will also be used. So del T del V times del V del U, so this is U constant, this is T constant, and then you have del U del T, volume constant, is going to be minus of 1. And this implies that I have del T del V, U constant, is minus del U del V, temperature constant, divided by del U del T, volume constant. Now let us go back to the first law, which we write down as du plus pdv. You immediately see that if volume is being held constant, this implies dv is equal to 0, and one has T del S del T, volume held constant, is del U del T, volume held constant. So you know what this derivative is, it follows from this, and if you recall, this is the definition of Cv. So that we write down this as minus 1 over Cv del U del V, temperature held constant. Now del U del V, temperature held constant, we use the first law again, T del S del V, temperature held constant, is equal to del U del V temperature held constant plus the pressure. So that del U del V, temperature held constant, is going to be T del S del V, temperature held constant, minus the pressure. Now here, when we have started off this calculation, we have assumed that we do not know the fundamental relation, which essentially means that S is a function of UVN, right? So we are handicapped in that respect, and we have to figure out this derivative by manipulating this derivative over here. So we have del U, finally we have del U del V as this. So now I have to figure out what is del S del V, T held constant. So this one, if I now use let's say F as U minus Ts, so that dF is going to be du minus Tds minus SdT, and du minus Tds is minus of Pdv, so that del S del V, temperature held constant, is del P del T, volume held constant. This is a very familiar derivative for us because I know that del P del T, volume held constant, del T del V, pressure held constant, del V del P, temperature held constant, is minus 1, so that del P del T, volume held constant, is going to be del V del T, pressure held constant, by del V del P, temperature held constant. With a minus sign in front, I multiply by 1 by V, I divide by 1 by V, the ratio remains the same, and this I immediately identify as alpha P, the expansion coefficient of the gas, divided by the isothermal compressibility, so that this answer gives me alpha P over kappa T. Hence, I have del U del V, temperature held constant, is alpha P over kappa T minus the pressure, so that del T del V, internal energy held constant, is going to be pressure minus, there is a minus sign overall over here, which means if I use this relation, this becomes minus of del U del V, temperature held constant, which is minus, and this is plus, so pressure minus alpha P over kappa T, 1 over CV. And this is the relation that you are looking for. There has to be a T over here because you're looking at T del S del T. So this is T del S del T, and there is a T over here. For an ideal gas, alpha P, which is 1 over V del V del T, pressure held constant, and I know the equation of state is NKBT. So which means del V del T, pressure held constant, is NKB divided by P. NKB over P is going to be, so let's just write down 1 by V, and then I have PV over here, and NKB over PV is 1 by T. So your alpha P for an ideal gas goes as 1 by T. The compressibility, the isothermal compressibility, is minus 1 by V del P, temperature held constant, and this means that del V del P, temperature held constant, is minus NKBT over P square. I will have a minus 1 by V, that makes it plus. Then I am going to write down this as NKBT over PV times 1 by P, and from the equation of state it follows NKBT over PV is 1, so that I have the ratio 1 by P. So you see, For an ideal gas, it follows that del T del V is going to be pressure minus temperature times alpha P is 1 by T and the kappa T is 1 by P, so that this becomes this and you have this 0. Hence, you conclude there is no cooling in Joule expansion for an ideal gas. dt, we come back to our original starting point, dt del Vu times dV, which is 1 over Cv, and then you have P minus T alpha P over kappa T times dV. So if the quantity in the bracket is positive, then there is heating. So the temperature of the gas increases. If this is negative, then temperature of the gas decreases. Right? So this is how you deal with this system if you do not know the fundamental relation. If you know the fundamental relation, which is S as a function of UVN, what you can do here is you can take the derivative del S del U to give you 1 over T, so that you can know T as a function of U, V and N. In which case your delta T is going to be T of U remains fixed, TF, VF, N minus Ti, U, Vi, N. This is how you will determine the change in the temperature. If you know this fundamental relation S. What is interesting to note here is, if I take this approach that I do not know the fundamental relation, but I want to calculate the change in the entropy, and the change in the entropy follows from the same way as we have calculated the change in the temperature, del S del V. U is being held constant, so I have the change in the entropy. We follow the same procedure as we have determined the change in the temperature. We write ds as del S del V, U is being held constant, times dV. And if you look at the first law, which was TdS was du plus pdV, then you see that del S del V, U held constant, is actually P by T. So that you have P dV over T. But P by T from the equation of state is NKB divided by the volume. And you have NKB divided by the volume, so that you have dV by V. Hence, the change in entropy delta S in going from the initial state to the final state is given by NKB dV over V, Vi to Vf, which is NKB ln of Vf over Vi. Surprisingly, there is a change in entropy, even though you do not have any change in, this is for an ideal gas. For a real gas, one has to substitute the equation of state over here. So this is for an ideal gas. We are looking at This expression is valid for an ideal gas, but this is the general expression that is valid for any gas or any hydrostatic system, except that you have to now, to proceed further with this relation, one has to replace P by T from the appropriate equation of state. Now this tells you that delta S is positive, so that there is a change in entropy. And the reason this happens is because this is an irreversible process. Your entropy is only defined in the initial and the final, not in the intermediate states. So you get an irreversible process where the initial and the final states are equilibrium states, but not the intermediate states, and therefore you cannot define an entropy. Now recall, for an ideal gas, the entropy had this expression 5, so we had NKB 5 by 2 plus log of V over N alpha U raised to the power N, alpha U by N raised to the power 3 by 2. This was the expression that we had, where alpha was a constant which is still not yet known to us, and we promised that we will determine this constant when we use statistical mechanics, but right now it suffices to have this expression. If you look at this, let's just first calculate delta S, which is the easiest thing to do. Then delta S is 5 by 2 plus ln Vf over N alpha U N raised to the power 3 half minus NKB 5 by 2 plus ln Vi over N alpha U over N raised to the power 3 half. Since essentially no heat and no work has been done, the internal energy for both the states remain the same, and you immediately see that this answer matches with the answer which you had obtained earlier, that this is going to be delta S is going to be ln Vf over Vi for an ideal gas. Since I know S, if this is my starting point, if this equation is my starting point, then I want to determine dt, the change in the temperature delta T for this particular system, which is essentially the ideal gas, and I know that del S del U is going to be 1 by T, and we have done this exercise. This essentially tells you that U is going to be 3 half NKBT, so that T is 2/3 U over NKB, and therefore you have T as a function of UVN from this relation. Surprisingly, for a real gas, for an ideal gas, it does not depend on the volume, so that delta T, it clearly follows, since it does not depend on the volume, delta T is going to be 0. So essentially this Joule expansion tells you that for an ideal gas, internal energy U does not depend on volume. A similar experiment is what is called a Joule-Thomson effect, which is also called the throttling process. And what the setup, what you have over here is you have two chambers which is divided by a porous media which allows for the gas to pass through. On this side of it, you have a piston and on this side of it you have another piston. The purpose of these pistons are to maintain the gas in the two chambers at two different pressures. So this one maintains it at low pressure and this one maintains it at a high pressure. So let's call this Pi and let's call this Pf. If I take 1 mole of the gas, let's call the molar volume Vf, and then the molar volume here on the left hand side is Vi. Now essentially you push the piston, so all the gas has gone from the left to the right. So it goes from left to the right. Now when all of the gas has moved to the right chamber, then there has some work has been done by the piston, which is this one, which is given by Pi times Vi. Now when all of the gas has moved to the right chamber, some amount of work has to be done by this piston which maintains the low pressure, and that is Pf times Vf, where Vi and Vf are the molar volume. So the net difference in the work is going to be the conservation of energy, tells me the change in the internal energy Uf minus Uy must be the net work done. I can rearrange this equation so that I can write down this as Pi Vi plus Uy is going to be Pf Vf plus Uf, where the small u's are the internal energy, the molar internal energy, just as the small Vi's were the molar volume. Now you immediately see that this means that for 1 mole of a gas, the molar enthalpy in the initial state, the left hand side, is going to be the molar enthalpy in the final state, so that the enthalpy, the molar enthalpy remains constant. The molar enthalpy in the not remains constant, but the molar enthalpy in the initial state is equal to the molar enthalpy in the final state. Please note that this is only a statement of the fact that the initial enthalpy and the final enthalpy remains the same. In the intermediate states, this is once again a non-equilibrium. It's an irreversible process, as we have seen in the Joule expansion. The enthalpy is not defined, so this relation does not talk about the enthalpies in the intermediate states, and this equality is not valid there. So now what I want to figure out is if there is a temperature change because of this process, and again we do it del T del P, motivated by our earlier work. Enthalpy constant times dP. This is a derivative which is very curious and which is not a standard derivative which we can evaluate very easily. So one has to manipulate this derivative. Of course, we do not know the fundamental relation. So then we start off by writing del T del P, but even before that we first write down, we have to look at the enthalpy, which is U plus PV, and dH is going to be du plus PdV plus VdP. This is TdS from the first law. TdS is going to be du plus PdV, so that you have TdS plus VdP. Now let's write down del T del H, del T del P, enthalpy held constant, times del P del H, temperature held constant, times del T del H, pressure held constant, is going to be -1. This is a cyclic relation which you have used several times. So del T del P, enthalpy held constant, is minus del H del P, temperature held constant, and then I have del H del T, pressure held constant. If I look at this expression for dH, pressure held constant means dP is going to be 0, and you see del H del T, pressure held constant, is T del S del T, pressure held constant, and this you immediately know is the specific heat at constant pressure. So I write down this as 1 over Cp del H del P, temperature held constant. Del H del P, from this equation itself follows that del H del P temperature held constant is going to be T del S del P temperature held constant plus V. So therefore evaluation of this partial derivative is equivalent to evaluation of this, and once again this is the problematic derivative, partial derivative that I have, because it's not in it doesn't relate to a standard derivative that we know of, any of like a response function. So we have to figure it out. Now you see I have del S del P. So let's try to figure out if there is a Maxwell relation. If there is a Maxwell relation that would give me what this derivative is, then you see this must be the differential of that free energy must have S dt and V dp. Whenever you see V dp, you know that you have to look at the Gibbs ensemble. G is equal to U minus Ts plus PV, and dg is going to be du minus tds minus sdt plus pdv plus vdp. So that du minus tds plus pdv is 0 from the first law, and one has minus sdt plus vdp. You immediately see the Maxwell's relation is del S del P temperature held constant is minus del V del T pressure held constant, and del V del T pressure held constant is a derivative we are familiar with because it relates to the expansion coefficient of the gas. So that del H del P temperature held constant is T del S del P temperature held constant. I have minus T del V del T pressure constant plus V, and this I write down as minus T by V times V del V del T pressure constant, and I immediately see that this quantity, there's a plus V, this quantity is equivalent to your expansion coefficient alpha P. So I have V common 1 minus alpha P times T. Very nice. So therefore this ratio which we started off with is del T del P, H held constant, is going to be 1 over Cp, V over Cp. This factor comes in over here. This is where you substitute this, so that this becomes V over Cp alpha Pt minus 1. So that dt is going to be V over Cp alpha P times T minus 1 times dP. For an ideal gas, alpha P goes as 1 over T is equal to 1 over T. We have just seen in our earlier calculation, and therefore this implies that dt is equal to 0. So this means that for an ideal gas there is no cooling, no heating, no change in temperature as the gas goes from the left chamber to the right chamber in the throttle. However, depending on the sign of this quantity, one can expect whether the gas can either cool down or heat up. So for example, let's take it very simply. This doesn't pertain to any system. Let's say if I have Cp going as A times volume, and I take alpha Pt minus 1 is equal to a constant which is equal to, let's say, B, and this is greater than 0. Then very trivially you see that dt is going to be B over A times dP, and therefore under these conditions dt, if I now integrate, you see, depending on the sign of B, it depends on the sign of B. If B is positive, B is greater than 0, which means alpha Pt is greater than 1, and provided this ratio V over Cp doesn't depend on pressure, it's just a constant number, then you see dt is less than 0. Why? Because if you integrate this, you're going to come up with a relation which is going to be Pf minus Pi. Initial pressure was high, final pressure was low, so this delta P is negative and therefore your temperature is negative, so the gas cools down. In contrast, when B is less than 0, your change in temperature is going to be positive, so that your gas heats up. So this means essentially the conclusion that we draw is that for an ideal gas, the internal energy U does not depend on pressure. In the earlier exercise, we have seen that it does not depend on volume, therefore U is only a function of temperature. Of course, we know this result, but nevertheless, if we had not known any of these things, that U was 3 by 2 NkBT, which followed from S of UVN for an ideal gas, we could have deduced all of this using these two experiments.